Oh yeah, I have to. Okay, so thank you very much for joining me on Zoom. So for this talk, I thought I would discuss some different aspects of the physics of shocks, more specifically relativistic shocks that are being corrugated because of perturbation in the pre-shock region. And because that's a situation that might happen in astrophysical environments, which is the application that I'm interested in. And I thought that I would try to discuss some very different aspects on different scales, so mainly macro scales and kinetic scales. So is it working? Yeah. So I'm going to start with a few words on the general astrophysical background that's motivating all of this work. So basically, we have compelling evidence that there must be some very efficient cosmic accelerators in the universe. The first most direct evidence of that is probably that we actually detect some of these accelerated particles. So that's what we call cosmic rays. So I don't know if you can see my cursor though. You can? Great. So this figure here represents the flux of like the all particle differential energy flux as a function of the energy per particle. And so you see the amazing large range of energies over which we detect these particles, and the incredible energy that these particles can achieve. And so we've discovered these particles for the first time, like more than a century ago, but we still are debating what are the astrophysical sources at the origin of these particles and what are the physical mechanisms that can promote particles to such ultra-relativistic speeds. And so up to like PeV energies, we kind of have a consensus that these particles might be accelerated at the shock of supernova remnants. But above these energies, it would be very difficult to advocate for the supernova remnant scenario. We would need larger, like more powerful sources with larger magnetic fields or spatial extent, because you need to be able to confine the particles in your source long enough to accelerate them. And so we have a number of potential relativistic sources that could be the particle accelerators. And those are mostly relativistic sources. So for instance, this little movie here is an observation of such a class of objects that we call a gamma ray burst. So this one was detected last October, actually. So this is a particularly bright and close gamma ray burst. So observationally, a gamma ray burst is, as the name indicates and as the movie shows, a bright point in the sky emitting first in the hard X-rays and gamma rays for a few milliseconds up to a few minutes. So that's what we call the prompt phase of the gamma ray burst emission. And then we have a longer afterglow over timescales of days, where we now observe emission on smaller, on longer wavelengths, so up to the radio sometimes. And so you can see how these objects can be powerful. They are actually some of the most powerful explosions in the universe. So the gamma ray burst is the point that you see here, and you see that it momentarily outshines our own galaxy here, when this object is estimated to be 2 billion light years away from us. So those are really amazing objects. And so the current standard model, sorry.
Can I interrupt?
Oh yeah,
Do you happen to know what the timescale of that movie was?
I think they had to gather data for 10 hours. Yeah. And so, yeah, the standard model that we have to explain these objects is represented in this picture here. So basically, we interpret these events as the birth of a black hole, resulting either from the merger of a binary system of compact objects. So that's what we call the short gamma ray burst, and the other pathway to this gamma ray burst is the collapse of a massive star into a black hole. So that's what we call the long gamma ray burst, and that's actually the scenario that we have for the little movie that I just showed you. And so basically, when these black holes are created, they can power relativistic jets that we believe might be hosting internal shocks that dissipate energy through some mechanism that we are still debating, and that could be at the origin of the prompt emission that I talked about. And then later on, the forward shock interacts with the ambient medium and again radiates energy that we can observe. So basically, these relativistic outflows seems to be a natural offsprings of systems powered by compact objects. So we actually observe them in very different types of systems at different scales. So we also observe such relativistic outflows, relativistic jets from X-ray binaries that I have not represented here, also in active galactic nuclei. So here we are talking about stellar mass black holes. Here we are talking about supermassive black holes of billions of solar masses. And another prominent sources of high energy radiation and a potential source of these cosmic rays that we've been wondering about is these pulsar-wind nebulae, which also emit relativistic outflows in the form of a wind that creates, again, a termination shock, a relativistic termination shock. So basically, the idea that I'm trying to convey here is that we know for sure that there must be some very efficient particle accelerator in the universe. We know a number of amazing objects with huge amounts of kinetic and or magnetic energy, but we still don't know how to explain from first principle how you convert this ordered form of energy into the non-thermal particles and radiation that we observe. And that's basically what I'm interested in. And one natural dissipation agents that people have been investigating is shock, just because they are so naturally produced in these relativistic environments, and also because of a theoretical reason. And that brings me to this concept of Fermi acceleration. So it's annoying because I don't see the entirety of my slide because, okay, I think I remember. So yeah, so this Fermi acceleration was initially proposed by Fermi in 1949, precisely because of this issue of the cosmic rays that we were detecting and that we were wondering how they were accelerated. And basically, the idea is that, okay, so you want to accelerate charged particles. I think I didn't mention it, but I hope you know that. So those cosmic rays are essentially charged nuclei, mainly protons. And so you want to accelerate charged particles. So the most naive way would be to imagine a very huge electric field that would accelerate it. But of course, astrophysical plasmas are highly conductive, and it's very difficult to sustain such large electric fields, except in very particular conditions, like in magnetospheres, for instance, black hole or neutron star magnetospheres. Maybe there you can have some electric fields, but the generic situation is that you have a highly conductive plasma and the charge are going to very easily screen out any large scale electric field. And so the idea of Enrico Fermi was to rely on motional electric fields. So say that these plasma have magnetic fields and they have a non-uniform distribution of velocity. So from there, so this is what I represent with this little picture here. If you imagine that you have a distribution of magnetized scattering centers, in the scattering center frame, you just have a magnetic field and the particle is just deflected, but its energy is conserved. But if you move back to the lab frame, you find that it has gained energy if it had a head-on collision, or lost energy if it was a tail-on collision. And because you have non-uniform distribution of the scattering centers, you cannot just cancel out the motional electric field by a uniform change of frame. So you will always have some motional electric field that can act on your particles. And because the interactions that lead to a gain of energy are more likely to occur, you observe a net gain of energy, even though the process is stochastic. So if you assume an isotropic distribution of your particles, you can compute the average momentum gain or energy gain as a function of the typical velocity of your scattering center. And you see that it's a second order relationship. And so initially, this picture was envisioned with the use of large-scale magnetized clouds that could be moving in the galaxy, but the speed of these clouds would be so small that by no account you could explain with that the cosmic ray that we observe. And now a more modern vision of this second-order Fermi acceleration is stochastic acceleration in turbulence, where the scattering centers are basically waves or turbulent structures. And an evolution of this second-order Fermi acceleration process is the so-called first-order Fermi acceleration, or diffusive shock acceleration. So basically, in the late 70s, we realized that in a shock, you have converging flows, and therefore you have a more a situation where you can more easily accelerate the particles, because if you imagine that your scattering centers are embedded in the flow, if you imagine that your particle can cross repeatedly the shock, whether it crosses from the shocked region to the unshocked region or the opposite, it always sees scattering center that's going to collide with it. And so it leads to a systematic gain of energy. And then you end up with the first order Fermi process. So that's basically why shocks have been for a long time considered as a prime candidate for the acceleration of particles in astrophysical environments. The problem is if you start trying to solve this problem from first principle, you realize that the things are not that simple, because you have well, first, you have a challenge of scales. Like if you want to be able to explain from first principle how a particle in the thermal bath ends up with energy of 10 to the 20 eV, you have to cover a tremendous large range of scales that's not possible to cover in any simulation. But more than that, it's just that the physics that govern shocks and particle acceleration at shocks is highly nonlinear and makes has different components that are in interplay with each other. So more importantly for the discussion that I'm going to have later, we have at least an interplay between the turbulence, the shock front, and the energetic particles. So basically, in the picture that I just showed you about diffusive shock acceleration, I told you if you assume that the particle can cross the shock repeatedly, then blah, blah, blah. But how do you ensure that the particles are indeed going to be able to cross the shock repeatedly? And basically, from kinetic simulations, the picture that has emerged is that the particles are actually able in some situations to generate the turbulence by themselves. And then this turbulence is going to influence their motion, their diffusion, and their acceleration. So that's first level of nonlinearity. When you start to have a large number of particles, the particles can actually modify the structure of the shock. And then you have also this interaction between the turbulence and the shock that we are actually going to be very interested in today. So basically, if you've got some upstream turbulence, it's going to go through the shock and be transferred in another, like it's going to be modified by the shock, and the shock is going to be modified by the turbulence. So it's a highly nonlinear problem that's very challenging to model. And we typically have different tools to use depending on what you are interested in. So the frameworks that I'm going to rely on today is like the kind of the two extremes that we have. So the first one is just MHD simulations, which adopt a fluid picture. So you no longer consider your plasma as a collection of individual particles, but you just look at kind of the average properties of your distribution functions. And in this picture, a shock would just like a shock without any disturbances in the upstream medium would just look like that. Like you would have an unshocked medium with some velocity, discontinuity, and then a shocked and hot medium. And so you completely discard how the kinetic energy of your flow is transferred, like is transformed into heat, and how you increase the entropy of your flow. You just have a discontinuity between an unshocked and a shocked medium. And if you rely on a kinetic picture, then we can start investigate how actually this energy dissipation is occurring at the shock layer. But then the scales that you can cover are very limited. You have, for instance, to resolve the skin depth of your plasma. And so if your motivation is to model astrophysical objects, you really realize that you're going to have to make some huge extrapolation work to make a connection because of this huge separation of scales. But anyway, like the general understanding that we have of these relativistic shocks is that their physics is going to be highly dependent on the Lorentz factor of the shock. So basically, we observe a very different behavior depending on whether the shock is relativistic or not. But then once you enter the ultra-relativistic regime, it looks like the dependence on the Lorentz factor is not so important anymore. And then another critical parameter is the magnetization, which basically measures the energy density of the plasma compared to the enthalpy of the plasma. So this is kind of a scheme where I'm putting the different astrophysical sources that I talked about earlier in this diagram as a function of the magnetization and the Raynes factor of the shock. But basically, yeah, we are interested in relativistic shocks, and I'm going to talk here about magnetization of the order of 0.1. So that puts us in this kind of potential astrophysical applications. And another point that I think I should mention is that these relativistic shocks are generically perpendicular. So perpendicular refers to the direction of the magnetic field in the shock frame with respect to the shock normal. So just because of the properties of the Lorentz transformation, like if you imagine a random direction of your magnetic field in the upstream rest frame, and you boost into the shock frame to compute the magnetic field in that frame, the components along the plane of the shock is going to be boosted by gamma. And so unless you have unless your magnetic field is aligned within an angle of 1/gamma in the upstream frame, you're going to end up with a magnetic field close to the plane of the shock. So in the rest of the talk, I will be always talking about perpendicular shock, where the magnetic field is perpendicular to the shock normal. And I think that's what I wanted to say. So yeah. My idea here is to discuss two, like the initial conditions, like the formulation of the problem is the same, but I'm going to treat them in two very different contexts. So one is in the fluid framework, and I'm going to be particularly interested in the response of a shock to upstream perturbations. And in the second part of my talk, I discuss about the effect of these upstream perturbations and the deformation of the shock that ensues can have on particle acceleration. So I don't know if I need that, but just so that we think about the same things when I pronounce certain words. So I'm going to talk about fast magnetosonic waves and entropy waves in particular. So basically, those are just the eigenmodes that you can derive if you linearize your set of equations of special relativistic MHD closed by an equation of states. You find that you can derive 7 eigenmodes. So basically, any linear perturbation in your plasma governed by the equations of relativistic MHD can be decomposed over these 7 eigenmodes, which are 2 Alvan waves, 2 compressible fast magnetosonic waves, 2 slow magnetosonic waves that I won't have the need of today, and an entropy wave. And so these dispersion relations that I wrote are in the race frame of the plasma. So this first issue that I want to discuss is somehow related to an old problem that was discussed in the plasma community, maybe like in the 60s, about the corrugation stability of shocks. So if you're interested, you can go have a look at these pioneer works by Dyakoff and Kantorovich. I think there is also some discussion in the Landau and the Lifshitz. But basically, when you talk about corrugation stability of shocks, you can think of 2 kinds of instabilities. So the corrugation instability, where you wonder if some small perturbation along your shock could make it repel exponentially. Of course, at least like in the linear stage of the instability. And another form of instability is the spontaneous emission, or the Dyatlov-Kantorovich instability, where your shock spontaneously radiates waves. And the problem that I'm going to discuss now is more in connection to this second type of instability. So the situation that I'm considering here is that I have a shock, initially planar, a perpendicular shock. So I consider, for instance, that the magnetic field is along the y direction. And I imagine that my upstream medium, or my unshocked medium, is carrying a perturbation. And throughout this talk, I'm going to use the most simplistic way to describe a perturbation. I'm going to say that it's an eigenmode of the plasma. And so we imagine that we therefore have an incoming MHD wave coming onto the shock. So then what happens is that the shock is going to get corrugated. In this MHD picture, you can simply imagine that if you have non-uniform upstream medium, it means that the shock jump relations now depend on y. And so on each position of your shock, basically, you can compute some jumping relations to compute the state of, or to compute the downstream state and the response of the shock. And so that's how you can easily imagine that your shock is going to get deformed, and you're going to induce outgoing MHD waves in the downstream. And the interesting observation to make is that for some wave vectors of the incoming wave, you will have resonant corrugation. And that's basically, you can draw a parallel to this spontaneous emission instability. So the idea of this project was to investigate numerically if we could recover this instability and this resonance, which has been derived in the linear, like using linear perturbation theory. So we were wondering if using a simulation with the finite amplitude waves, you could be able to recover this instability. And so that's the kind of simulation that we did to investigate that. So the initial condition is like the scheme that I showed you earlier. Like if you're in MHD, you don't have to work out the physics of the shock transition. So you can just form a shock as an initial condition. You can just decide what's your initial state of your upstream is, what's the velocity of your shock, and you can just solve analytically the Rankine-Hugoniot relations, and you determine the downstream state, and you can just use that as an input for your simulation. And if your code is robust, then nothing happens, because it's just a stable solution, and you just see a shock standing there. Because yeah, I'm going to work in the shock rest frame because I'm interested in studying the response of the shock. And so we add the perturbation that we want to interact with the shock. So basically we use the boundary conditions of the simulation box to input the wave, and then we just let it flow with the upstream and interact self-consistently with the shock. So the wave that I'm considering here is an entropy wave. So basically it's just perturbations in the density field. And it's like a moderate amplitude wave. And so that's what a simulation looks like. So the upper panel is the density, the middle panel is the magnetic field along the initial background magnetic field, and this is the velocity along the x-axis. So basically what you see is what you could already expect from just theoretical consideration, the shock gets repelled, and you kind of see a superposition of waves being excited in the downstream. And so then to investigate the existence of that resonant response, what you can do is compute the amplitude of the deformation of the shock as a function of the amplitude of the waves that you use to deform the shock. And a resonance would translate in a very high amplitude compared to what you use to excite it. So that's basically what I represent on this plot. So the black curve here is the ratio of the amplitude of the corrugation of the shock as a function divided by the amplitude of the incoming wave. And this is the wave vector where we have the resonance, where we expect to have the resonance. And the points are results from simulations for different amplitudes. And so basically, we see that in particular for low amplitude simulations, we really have a good agreement with the prediction from the linear theory. And what I plotted in my panel, in this panel below, is the velocity of the component of the velocity along x of the fast magnetosonic mode that's excited in the downstream. So that's the magenta curve here. And the horizontal curve here is just the velocity of the shock. So here this is computed in the downstream frame, both. And you see that the resonance happens when this fast magnetosonic mode is traveling with the same speed as the shock. So basically, we interpret this resonant corrugation as fast magnetosonic mode excited in the downstream and happening to have a group velocity that allows it to surf on the shock and allow it to be maximally deformed.
Yeah, I have a question. So which direction is the group velocity of the outgoing mode? Is it propagating opposite to the left in this picture?
So in this picture, it's moving because I mean the shock frame, it's almost like stationary, like it's just able to surf with the shock. So like the resonance is really where the group velocity along x is the same as the shock.
I see, thanks.
So yeah, how minutes? Okay. So to conclude this first part, we basically,
Camilia, excuse me, sorry for slowing you down here. Could you, I mean, the last couple of slides were kind of very unfamiliar to me. I'd like
to sorry. Yeah. Feel free to interrupt me because like.
KX, so what you have here, if I understand correctly,
is the longitudinal wave number of the incoming wave.
So this is not a single simulation, right? This is
exactly each point is a simulation. Exactly.
And each simulation has only a single wave in the upstream region.
Exactly. And so here it's an entropy wave. Yeah. And so here on the x-axis, you read the longitudinal wave number, and the color tells you the amplitude of the wave.
Color tells what? The color tells us the.
So it's the magnitude of the shock deformation divided by the magnitude of the wave that I used in the upstream region. So the magnitude that
you have. Sorry, let's go back to the.
Sorry,
can you? So here you have, just so that I understand. So the blue, there are blue, red symbols. So red symbols when the perturbation is small.
Small.
And the black line is the analytical theory.
Yeah.
That
And this one you can ignore because it's more relevant for another type of waves, but for entropy waves, it's not very.
So the linear theory comes from where?
So if you want to know exactly, you can look at this paper. So basically, you really solve analytically. So you have like your input data is the velocity of your shock and the properties of your incoming wave, and then you solve the Rankine-Guignol solutions to determine. I mean, more precisely, you solve the linearized SRMHD equations and your
special relativistic MHD.
Yeah, and your unknowns are the amplitude of the shock, and it's just a polytropic equation of state. And yeah, your unknowns are the amplitude of the shock and the amplitude of the different eigenmodes that you can have. And when you solve that, you get everything. So you can actually predict the amplitude of the different waves that you're going to have, and more importantly, the amplitude of the corrugation.
So you have a single wave coming in, and it does two things. One is it corrugates the shock, so it does something to the shock, and then another question of interest is what happens to the wave itself. And as I understand, you're saying
it's transmitted, so it's like a refraction problem, like you have an incoming wave, and
it can convert into different types of waves, right?
Yeah, exactly.
Okay, I see. Thank you. Okay.
Sorry, yeah, really feel free to interrupt me because, like I said, I haven't prepared as much as I should have, so I might like forget to say obvious, like very important things.
So this is for that, well, because the whole setup sort of is unfamiliar, but it's
yeah. So yeah, so I try to use the most simple setup. So then yeah,
very
you
much
can
appreciate it. Yes,
you can do the same for different waves, for different kinds of waves. So that's what I was coming at in my conclusion. So here I just showed the most simple wave that you can have, which is an entropy wave. So only perturbation in a density pattern, but you can do that for different types of waves, and the phenomenon is really the same. Like you always find at least one longitudinal wave vector that's going to lead to the generation of a fast mode that happens to travel with the shock, and that's where you have this resonance phenomenon. It's also universal
Camilia? Sorry, I have a question on the previous slide. Can you go back? Yeah, what is suppressing the resonance in the nonlinear limit? Like when the
yeah. So I mean, it's I think it's something that we often observe. I think when you move to the nonlinear regime, so there are two possible explanations. So one is that my setup is kind of less clean when I use these large amplitude waves. So like I said, the way we compute this black curve is that we compute the input parameter is the initial wave, its amplitude and wave vector, and then you compute the deformation and the outcoming waves. Now, if you start using a large amplitude wave in your simulation, you can have some mod conversion. Like those are linear eigenmodes. If you start increasing the amplitude of your wave, it's no longer an eigenmode. So you can have a mode conversion that happens between the time you launch your wave here and the time it actually interacts with the shock. So that's one source of smoothing out the resonance. And then, yeah, I think it's just that the response of the shock is it tends to have a deformation of the order of the amplitude of the incoming wave when the amplitude of the wave becomes large because of the order of unity, basically. So you cannot like completely disrupt your shock by sending a large wave. You will just have a response commensurate to the wave that you're sending. I don't think you can observe this resonant phenomenon with a large amplitude wave. But I mean, like to really answer this question, we should find an exact solution of the nonlinear mode, so that we would be able to simulate it and then we can see. But yeah. Yeah, and so like the potential interest from an astrophysical point of view would be to, and so that gives some future perspectives, would be to see if that can help to dissipate some energy in the shock, because in the context of these highly magnetized shocks, where as I'm going to show later on, the fact that you have such large magnetic fields, you can't accelerate particles. Maybe the fact of corrugating the shock could help dissipating more magnetic energy. So that's an issue that we haven't properly investigated. And then of course, impact on particle acceleration is of great interest. And that's basically the motivation of this next work that I'm gonna. How long have I talked? Because I'm using my phone. But, okay,
you've got another 13 minutes.
Okay. So yeah, I'm moving on to this second part of my talk, where I now leave the fluid picture to move to this kinetic picture, where we can now self-consistently investigate how the energy is dissipated, how the transition layer is actually formed. But then, yeah, the cost for that is that we will only be able to cover very small scales, spatial and temporal scales. But if you're interested in particle acceleration, that's the most self-consistent way of doing it, because then, of course, you model your plasma as a collection of macroparticles. So you still have particles in the picture.
Get it in my ear.
I don't know. Has someone asked something? No. Okay. So yeah, the motivation is basically that, well, first, it hasn't been done before. So most of the previous first principle studies of shocks have focused on the ideal situation where the shock is initially homogeneous, like the upstream medium is initially homogeneous. And it's a very idealized situation from astrophysical standards. So I think it's worth wondering what happens if you break this assumption. And then, yeah, the other motivation is that the result of these studies considering homogeneous media has gave rise to this paradigm that basically non-magnetized or weakly magnetized shocks are relativistic shocks. I'm always talking about relativistic shocks, are good particle accelerators, while magnetized shocks only produce quasi-thermal distribution. And the reason is related to this superluminal configuration of these magnetized shocks that I briefly mentioned in the introduction. So basically, that's what I try to represent in that dirty drawing here. So this is the upstream region and the downstream region. And the way we simulate these shocks is that we send a flow with a certain velocity. So here it has, in the simulation that I'm going to show, it has Lorentz factor of 10. And we have a reflecting wall, and the particles are reflected there. And by having an interaction between the incoming flow and the reflected flow, we manage to form the shock from first principles. So the initial condition when you consider a homogeneous medium is so the bulk flow, the background magnetic field. Typically, if you consider 2D simulations, like 2.5D simulations, people tend to consider out of plane magnetic fields. And then we have the electric field minus v cross b that we use to cancel the drift that the particle would have around the magnetic field. So that's how we managed to have the particles going in straight lines. Now, when you have your particle, so the red line here is supposed to represent the shock that has formed, and we just forget about the fine structure of the shock. What happens is that the particle comes from this region where it was feeling a small magnetic field, and more importantly, its drift was cancelled out by the motional electric field. It gets in this region where the magnetic field is compressed, and the motional electric field has almost disappeared, because the downstream is approximately at rest. The simulation frame is that of the downstream. So then the particle starts to gyrate, and the shock is basically moving to the velocity close to the speed of light. So the particles just have this kind of trajectories. They just coherently gyrate when they arrive near the downstream, and the shock just continues moving away, and the particle never gets a chance to cross back the shock again and do this multiple crossing that allows it to have to sustain particle acceleration. So those are snapshots from such a simulation. So the magnetization is 0.1, and these studies have basically found that for magnetization above about 10 to the minus 3 for pair plasma that we are considering here, you just observe quasi-thermal distribution in the downstream. So that's why I'm using a magnetization of 0.1, where I know that in absence of perturbation, I'm just going to have a quasi-thermal distribution in the downstream. And so the structure here is typical of a magnetized shock. So here, this is the density. So if you remember from a few slides before, when I was comparing the fluid picture and the kinetic picture of the shock, we had a much more smooth shock. So that picture was from a low magnetization shock. It was a snapshot from a kinetic simulation of a low magnetization shock. For large magnetization, because of this behavior where it's just filled the compressed magnetic field and particle starts to gyrate coherently, you have this very abrupt transition between the unshocked medium and the shocked medium that also appears for the magnetic field. And so now this is the comparison of the same shock, where this time, so here, this is the picture from the previous slides, the planar shock, the one that has been already simulated by many people before. And this picture here is when I used as initial condition a plasma carrying density pattern, exactly like I did for the MHD simulation I showed you in the first part. But this time it's with kinetic simulation. So what we observe is that, again, the shock is going to get rippled just because of this non-uniform upstream conditions. And you observe the development of like turbulent streams in the downstream. So basically, like you can track the history of the evolution of the downstream structures by moving along the x-axis. So the further away you are, and the longer it has had time to evolve, because again, we are working in the downstream frame. So the shock is moving like that, and this part of the downstream has been formed before this part. So basically, when the wave impinges on the shock, it creates an alternation of high density and, oh, my power is back. But yeah, a bit later. So it creates an alternation of large density and low density plasma. the same pattern is observed if you look at the bulk velocity of the plasma. That's unfortunately not represented here. So you can imagine that where you have this alternation of high and low density pattern, you have the same kind of pattern imprinted in the bulk velocity, just because of the conservation of matter. And so this alternation of layers of low and high bulk velocity is gonna create some shear and excite some kind of Kelvin-Helmholtz instability and create the whirls that you see here that then tends to merge over time.
Camilia, there's a question in the chat. Are there considerations of convection and magnetic field?
There are considerations of convection in magnetic field. I'm sorry, I don't understand.
Do you want to clarify the question?
Yeah, there's just I guess like in some MHD equations or in fluid dynamics, there is some considerations of convection, like if the magnetic field is convecting and how that affects the dynamics of the system. That's what I was just curious about, but doesn't sound like it, so never mind.
Okay.
Positive convect, in what sense is it? It's
yeah, I don't even understand the. I don't know how, like, you have a modified equation to include some convection effect, or I don't know.
Yeah, because sometimes you can like I don't know, because I don't know if you guys are using like the Prandtl number, and then you can take into account like if it's convecting with like Reynolds or Prandtl numbers, but never mind.
Okay, so like the MHD simulation that I was talking earlier about were just ideal MHD simulations, so there were no explicit resistivities or whatever, so all the dissipation that was occurring was of numerical nature and not
presumably was very small, or I mean the resistance.
Yeah, they were like high resolution
of course magnetic field was convected by the flow, right? But Camilia, I have another question, if you don't mind. So you said that here in the peak simulations, you used exactly the same setup as in the MHD simulations.
I mean, yeah, maybe, yeah. I don't know
but
if
one
exact is...
No, okay, but one difference that I see is that in the MHD simulations, what you showed were these, entropy wave that was oblique. I mean, what had some sort of random, not random, but some general angle relative to the shock. And here I can see that, I mean, according to the
so I think like
panel, there is no K, there is only KY, but not KX.
Yeah, so there is, but it's very small. So like I think I have a factor of 100. So basically it's so how to say so in the MHD simulations, we were actually interested in the angle, because depending on the angle, we observed the resonant response.
Right.
Here we didn't really care. We just wanted to corrugate the shock in some way, and see how it affects particles. We were not really interested in, but yeah, so that's for like for future works. Yeah, we can.
That was precisely the reason I asked, because this the resonance condition that you wrote down there involves KX. And here KX is 0, right?
Yeah.
Okay.
So yeah, here really we didn't care about the resonance, and like I don't know if we'd be able to catch it with the kinetic simulation actually, but yeah, we just wanted to corrugate the shock and like create some downstream turbulence and see how it affected the particles. Okay. So we just found that if you use a very large number for the ratio of Kx and Ky, it doesn't matter which number you use.
Thanks.
So the plots below are the particle. So I'm going to start, let's start with the one on the left. So this is the particle spectra that I observed for different amplitude of the incoming wave. So delta rho over rho zero, rho naught, basically. So the blue dashed line, delta equals 0, is basically the planar case. So it's the one that we get from this picture, and it's basically the one that you can find in the many previous studies. And yeah, you see that you have essentially a quasi-thermal distribution of particles. The inset shows the maximum energy of the distribution. And so basically you see that it's just a plateau, like, so these spectra are taken in a slice of the downstream, and we just compute so here we have the particle spectra at towards the end of the simulation, which is about 2500 plasma times. Relativistic plasma times, and yeah, the inset shows the maximum energy of the particle in this slice of the downstream that we selected. Like I think it's from 400 to 900. Like we just selected a slice in the downstream and computed the particle spectra. So yeah, blue line is a plain case, and basically the boring result that we don't observe any energetic particles. And then you have the different spectra for different amplitudes. And so basically what we observe is that the larger the amplitude of the waves, the more you basically deform your shock and excite a strong turbulence in the downstream, and the more you are able to create energetic particles. And the plot on the right compares the influence of the wavelength of the wave that I used to deform the shock. So again, blue line is same simulation, planar case. So it's as if the wavelength tended to infinity. dE is skin depth. And yeah, again, we show for decreasing wavelength, it seems that we accelerate more particles. And the way I understand this is that it seems that it's mainly a resonant phenomenon. So when particles have a Larmor radius comparable to the size of the downstream structures, they can interact with them and gain energy in a stochastic manner. And these structures tend to grow in time. So it seems like if you start with small structures, you will be able to have a larger range of energies. You will be able to start like the injection energy of your particle in the acceleration process will be smaller, and then you can accelerate the particles as their Larmor radius grow in time, because the structures are merging and getting larger. And so I'm almost done. This is just a movie of such a simulation. So upper panel, yeah, I forgot to put the quantities. So upper panel is density in units of the upstream density, and lower panel is EY. So maybe I can start from. So what we observe is basically that we have an initial jump in energy compared to the planar case, because the particles are able to return once in the upstream before going in the downstream, unlike in the planar case. And then we have this electric field going in this direction. So when the particle crosses the shock and is able to go back in the upstream, it gets accelerated during this half gyro motion. And then once it's in the downstream, it's just kind of interacting with the motional electric fields that are created by the velocity fluctuations. And so let's see, like if you look at the blue particle, for instance, you see basically that when its gyro motion is kind of in line with the structure of the electric field, it can get accelerated. On the other hand, for instance, if you look at the orange particle, it tends to be always in the same patch of electric field. So then it means that during its gyro motion, it's going to be accelerated and then decelerated just because it sees basically a uniform electric field. So we really see this slow increase of electric fields when the particle is able to experience different kinds of like regions with different electric fields, so that it doesn't cancel out during gyro motion. Okay, brief summary of the first part, where I discussed the physics of shocks really from a fluid picture, and I was just interested in the response of the shock. So that's why I worked in the shock frame, in the shock rest frame, and not in the downstream frame. So we couldn't really see the time evolution of the downstream in this simulation. But yeah, basically the takeaway message was that you can have a resonant corrugation for certain wave number of your incoming wave when you excite in the downstream a fast mode that travels with the shock front. And in the second part that I just showed, I try to explain how these previous simulation, considering initially homogeneous media, have given rise to this paradigm of relativistic shocks being good particle accelerator in the weakly magnetized regime. And our work suggests that for the very simple situation where you consider density perturbation interacting with your shock, so you have density perturbation that are not able to accelerate particles by themselves, interacting with the shock that's also known to not accelerate particle when it's by itself, seems to produce interesting situations that might allow producing energetic particles. It's just motivation to further investigate this issue, I guess, because the simulation that I showed were not that long, like I said, 2,500 plasma times. So we need longer simulations and a more extensive parameter study. I just focused on given magnetization that I knew was not accelerating particles in the planar case, but a more extensive parameter study is certainly needed. Thank you, and sorry I was a bit long.
Thank you very much. I think
thank you very much.
Impose on Camilia a bit longer. Any of you have questions, please ask them either in the chat or just speak up.
Well,
yeah, Dimitri, please go ahead.
Thank you, Greg. Thank you, Camilia. Very interesting talk. To me, it was a novel and unusual problem with which I wasn't familiar. I was very familiar with just regular shocks that you said that the paradigm for the initially homogeneous media, but this interaction with different waves. So I'm just wondering whether you've envisioned this as some sort of large long-term program, research program of systematic study of, because you can have different waves, right? I mean, just so you know, you could have different types of single waves, right?
Exactly. So we did that in MHD because it was very easy to do. And so in particular, if we want to scan a larger magnetization, I don't think we can stick with density perturbations, because then the energy perturbation represented by your density wave is going to be negligible if your plasma is magnetically dominated. So you need to have magnetic disturbances. But then, so I did try actually to run magnetosonic modes but I had just like numerical issues. I had trouble having a stable magnetosonic mode, and it's not obvious to me that we can actually simulate those with kinetic simulation. Like, so I just used the ideal image depolarization and just put it in my code and saw what happened, and it was not very stable. So I don't know if it's because it was a large amplitude wave simulated with a kinetic shock, whereas it's a MHD solution, or if it was another issue. But the other thing is that I really think that if you want to make astrophysically relevant conclusions, you want to be able to run long simulations, and that has proven to be difficult. But I do think that there is some potential, because I mean, like, just plain density waves that cannot do anything by themselves seem to quite change the picture. So
yeah, particularly important. But I mean, just from the basic physics point of view, I mean, there is a simple question of, even for the linear waves, small amplitude waves, you can sort of just ask what happens to the wave, what comes out on the other side, right? You can have an Alfvén wave at a certain orientation, certain wave number, and see what it turns into.
Yeah, so yeah, in the MHD in the MHD framework, yeah, that's definitely the picture that we get. Like, when you look at the MHD simulation, you can almost see by eye the superposition of wave. It was not as turbulent as we had in the kinetic simulations. So I don't know if in kinetic simulation you can actually have these Alfvén waves or fast magnetosonic modes being excited at these kinetic scales, like, unless you're using a huge box. So I don't know, maybe you can, maybe, I don't know. So yeah, that's one thing. I think it would be interesting to like analyze the mode content of the turbulence excited in the downstream. See if you can recognize some maybe image diagon modes. I don't know. But yeah, in the kinetic picture, because you do simulate the physics of the shock layer, and I do feel that it's being affected by the incoming wave. Yeah, it seems like a more complex problem that in the MHD, where the shock is just a discontinuity.
Yeah, but it seems like, as I understood correctly what you showed, when you showed the spectra, the resulting spectra for different wavelengths, it seems that the effect on right, exactly, the lower right plot, this particle acceleration that you found is only significant when the wavelength of the density perturbation is sort of gets into smooth kinetic scales.
Yeah.
Right. So becomes comparable to D in this case. Is this troubling or not? I mean, because if you kind of envision applying this to some turbulence or some sort of macroscopic waves, right, they would have small effect, right, according to this.
Yeah, so then, I mean, so like I said, at least in what, so maybe if we were able to run very long simulation, we would observe some form of non-resonant acceleration, and then it could work, even though the the wavelength of the perturbation is longer. But in this third simulation, yeah, it's really dominated by resonant acceleration, and then that's, I think, but I mean, I take oratory caution, like it has to be further investigated to claim it as the truth. But what I think is that, yeah, the reason why the effect is more dramatic for a shorter wavelength is just because then you can, like the particle that have a small Lambda radius, like that are in the middle of the thermal bath, in the middle of the thermal distribution, have the right Lambda radius to interact with the perturbations, and then these perturbations grow in time because they merge together, and then they can affect the particle that have been accelerated and have their Lambda radius grow. But that, I mean, yeah, that's the picture I have, but yeah, I should stress that it has to be confirmed.
If you have cosmic rays already upstream, they may be, so even if you have
and then yeah, exactly, like now if you start with a cosmic ray that already has a huge energies, like it has been, like it's coming from a supernova remnant and it's been accelerated to already high energies, then it has a large Larmor radius, and then it could even resonantly interact with the perturbations excited by a large wavelength perturbation. So yeah, that's also one project that we had in mind at some point, actually, just to run MHD simulations with test particles. Then you can inject them with the Larmor radius that you want. And yeah, it would be interesting to see if we observe the same behavior.